Today some more aspects of physics, and then we will be merging our towards the development or design and development of the real electron gun. I thought that I should share some drawings with you first, and then we will be switching to the actual presentation. So this is a bit of physics that we will be needing. Unfortunately, I could not cover these things yesterday. You can see it. Consider that you have a plate and you have connected it, a pair of it rather. You have connected it with a power supply. So there will be an electric field established here. The potential lines actually follow the geometry of these electrodes. For example, because they are like parallel and straight, so that's why they are the parent and the lines which I've drawn are like parallel to them. For example, if I had a geometry like this, the potential lines will be like this, okay? And of course, if on the other side, they will be looking like this. What if I want to draw the electric fields? Electric fields are always perpendicular to the potential lines. This is a key to the optics. Okay? Similarly, on the other side. Maybe you can take a picture of it. Another concept that is very essential is the introduction of apertures. Consider that we have three different apertures. You're familiar with the apertures, are you? It's just a disk with a hole, maybe an old-fashioned CD. Okay, so I have connected, let's say, it to a certain potential, and these neighboring plates are grounded. So what should be the value or the shape of the potentials in this case? Let me draw. Let me draw it and then I will discuss. You see, why have I have drawn it and not straight this time? They are bulging towards the region where the potential, for example, if this is V1, this is V2, this should be also V2. So V1 is very much higher than the neighboring potentials. So the field lines or the potentials are bulged towards the weaker potentials. Okay? This should be in your mind. And what about the electric fields? By the way, this makes lenses. Okay? The electric field lines will, of course, look like something like this. Now imagine that we have a beam coming, any charged particle. By the way, I'm talking about these are electric fields. Okay, so they will they will be focused because this the shape of these potentials are very much like the optical lenses, which focus the beam on a point, and beyond that point, the the beam again diverges. So this beam will actually follow the electric field. It will focus, and then it may be, if not set equally, it will diverge again. Okay. So I thought that you should have this in your mind. Maybe you can take notes of it, and then we switch to the actual uh, presentation, the PowerPoint presentation. Oh, my drawing is so poor. I'm not used to this. Let's get it. So, did you have time to take a look on the homework problem? No, that's just nice, I guess. We can discuss if there is any things need to be clear. Okay. So, we have almost 60% of this working day dedicated to the design, manufacturing, testing, and characterization of electron guns. Sir, can you kindly minimize that screen so that we can see the whole picture? So when I say that thank you. No, when I say that we have to design, it means the physics design and the engineering design. Both come under the definition of design. We are perhaps now well equipped with the essential tools that are required for physics design. I am not a mechanical engineer, so I can just share with you a few drawings. I may not be able to detail everything that is involved in the manufacturing, but I can go through the mechanical aspects of the electron gun. Then, which is also involving this step, the manufacturing. Manufacturing, in fact, has many steps. First, the electron guns are manufactured in parts, and I haven't seen any like big electron guns that are machine made. They're always handmade. I mean, it's more than art to collect the components and fix them in a single assembly. So in fact, every electron gun is unique, except those commercial small triodes, and because they are manufactured in larger quantities, so they are machined. Then you have to test and characterize the electron guns. When I say test and characterize, it means that I should have a complete setup of measuring some parameters. And if you remember, on a physicist's point of view, that character is summarized in a single vector that is called a state vector. So in fact, when I say testing and characterization, this is a hardware part and this is the physics part. Okay. If only then I am satisfied that, okay, I imagine something that I want to develop, And that imagination was, in fact, mathematically translated in the form of a vector. So I will actually see how my theory is like synchronized with the actually manufactured. Okay. All right. So our client is the end user, the Electron people, the Linux people, or some other guys who want us to design a source which is well suited for their requirements. So we are nearly convinced because we saw it in detail yesterday that is a matrices, and all the matrices actually act upon our initial vector and then the final vector instead. So in our case, we want to, for example, devise something that can generate very high power. We will need very high current density. No need to repeat, I guess, today. Low emittance in transverse direction means that it should be very well collimated. It should be parallel, not tending to go here and there. It should be very well focused. Okay. And stable operation. I haven't talked about this because this comes nearly under the development phase. Okay, you have developed a gun, which is very nice. But what if it works some days, it doesn't work the other day, or it has a mood swings or something? So the operation should be very, very, very stable and reliable. For example, if there was a practical joke. So if you have a radar and this something is installed, the Electron gun is installed, and the gun is not working. So and the enemy just come, and it will not give you some time any time to like fix your things. So you have to be prepared. It should be reliable. And the DC and pulsed operation. When I say DC is a continuous operation, you're generating electrons and you're just accelerating them and using them. Sometimes you have to give pulse operation depending upon the requirement. For example, Clastrons and Linux, they prefer to operate their sources in pulse format. And then longer lifespan in case of operational life of cathode. Cathode, perhaps in my experience, is the only like part which has a shelf life. All the rest, if not hammered to death, can last for decades. So because the cathodes which are nowadays used are either eroded or they are exhausted with the supply of impregnant. We use barium oxide with tungsten to enhance the emission. I will talk about it in detail, but the supply of barium is not limited. It's just like the supply of ammunition for a soldier, and because it's limited, so the bullets are limited for you. You can fire at them unless you're exhausted with the supply. So the client would always want that you design an electron gun which has a longer lifespan. Nowadays, we are lucky that we can have very reliable dispenser cathodes, which can last at least 10,000 hours, operational hours. You can like translate it into years, so it's a reasonable lifetime. But it depends on the use. It depends on the use. If I dip my bullets in water, they will not fire. I mean, they're gone. So similarly, you need to have certain operational conditions for reliable and suitable operation. So whenever you provide your electron gun to a certain client, you give a manual of operation. Okay, operate it under these conditions, only then I can guarantee the reliable operation. We will discuss this point in a reasonable detail today. and ease of operation, lesser control parameters. Okay, in laboratory or in some controlled environment, you can have a liberty of playing with the parameters. In fact, we do as experimental physicists, we have lots and lots of things to control, but these things are never bothered by some end user, especially perhaps forgive me if I'm biased, especially the operational engineers. They do not say, okay, they just want to have a button on, off, on, off, on, off. That's it. And every time they want, they say, okay, I need the beam. I don't want to know the physics behind it. Okay, so we have to provide something that is lesser bothering and low operational and maintenance cost. This is perhaps the point which is more like commercial point. And in fact, we had the same problem. You're always limited with money. What we did was, for our Linux, we devised electron gun assemblies that have replaceable parts. In fact, you can always take out the gun. Maybe you have never heard that a small machine like 6 MeV medical Linux should have an electron gun which is replaceable. Always Siemens, giants like Siemens, General Electric, or Varian or something. They provide you machines which have guns already brazed with the structure, fixed. But guns can go away in milliseconds. So your whole machine is dead. And guns can last for years and years without any bother. It's just your luck, maybe. Perhaps more than luck, it's the operational expertise that are required. So since we were not we are still not very expert, but we've opted for a replaceable part, replaceable guns, and they effectively paid back. We had 3-4 accidents. I will show you the scenarios at the end of when I will discuss the practical aspects of the operation. We were at the end of the project. A certain milestone was being achieved, and then suddenly the gun went away. It was a shock. But since we planned earlier, within 3 weeks, we were back. But what if the gun was already brazed? So that would have been a disaster. We had to start from the scratch. Manufacturing takes months. Yeah, and it's very expensive. So you can, if you know how to design, you can cover almost all these steps. But how do you do it? This is the slide for designers, an exhaustive list. This is perhaps few points, but for us, or the people who design electron sources or plasma sources at some point, it is complete R&D. So perhaps you first start with the physics design, and that design should cover high current, low transverse emittance. Now you understand this point quite well. Choice of electron emitters. Okay, the client is asking me that much current. Where should I go? Should I just go for the tungsten? Because every metal can give you electrons. Okay, but what is more commercially viable? We started with tungsten, huh? But is it okay for the commercial guns? We'll discover. What should be the operational mode? Maybe pulse and DC, they are combined these days. I mean, every electron gun is supposed to work in both these modes. And if it is in pulse mode, even the very high duty cycles are expected. I mean, you have to operate it on very high frequencies. Okay, system designed for low voltage and high voltage operation. Oh, okay, someone will always ask, okay, you have a gun, how will you operate it? You need a full bunch of power supplies, which are to be reliable. There are two main parts of the power. One is the low voltage power, that is for heating, and high voltage power, that is for the acceleration. And everything is vacuum sealed. When I say vacuum, I hope you all understand the basics of vacuum. Fortunately or unfortunately, we have to maintain at least ultra high vacuum conditions for reliable operation of electron guns. Extreme ultra high vacuum is essential, in my humble opinion, for activation of the gun.
What is the rate in terms of torque? 10 to minus 5 torque?
I will discuss it in details. No, the extreme ultra high, if I want to start the electron gun, means activation, it should be at least 10 minus 9 torques.
10 to minus
9. It's in the operational range. I would start with low 10 minus 8, but my threshold I always set around 5 minus 7 torques, millibars. Beyond that, it's poisoning. It's killing.
Is it necessary for each time to reduce the torque to the 10 to minus 9 level?
No, for the first activation. Yes, first activation. This is very important. I have a dedicated couple of slides for this point. Then, how do we know? This point looks now very humble. Perhaps occupies 1% of the slide, but this is where the diagnostic and commissioning, the evaluation of the which vector? State vector comes. Okay. Now the designers or engineers will cover the realization of physics design and get it manufactured. Believe me, I have an engineer. He's a very good friend of mine. But when I went with the physics design to him, okay, he was almost in a mood to kill me. Okay, what you have brought, it's machinable, okay. But eventually we got it machined, because the profiles which we suggested for this morning, I show you the drawings. The profiles of the lenses, the optics can be very complex for a gun. So that complex realization can be a nightmare. And the choice of materials, you cannot always go for anything if you are going to manufacture electron guns. Professor has asked a question: what sort of vacuum you need? Vacuum can be deteriorated by many aspects. If you are using some material that is degassing or degasses at some point means at some temperature, then the whole assembly is useless. I mean, you lost your vacuum. So the choice of material and manufacturing schemes, they are very, very important. Once these things are done, we have to assemble it, and we have to assemble ideally in a clean room of reliable cleanliness. And most of high-end current guns are handmade, as I mentioned. So it's more than an art. You have to spot weld the things, the heaters especially. You have to be very like a jewelry making business. It's like, or maybe a neurosurgery. Usually for us, it takes around a week to assemble an electron gun. Okay, and then the assembled parts are tested to check.
Can I ask you something? You say parts are cleaned and handled in a vacuum compliance manner.
Yes.
In a vacuum environment, parts?
No. It means that you should have ideally the clean room. The clean room. Vacuum compliance means that, okay, when I was a student, I went to CERN and I tried to touch something with their bare hands. And there was a graduate student. The professors are very humble. They will teach you, yeah, you call yourself vacuum guy and you don't know how to wear the gloves. So you should be disciplined and patient while working with the vacuum. My hands they're always sweating. and so does your hand, because they have minerals which are killing. They have water, OH. Allah subhanahu wa ta'ala has ordered water to give life. It will penetrate to every corner of the universe. But for gun, it is not required. OH molecule is the most adhesive, in my opinion, and most difficult to get out of the system. So,
what kind of clean room you need for class?
Perhaps you have already worked on, maybe you can, because it's the number of particles that are tolerable are 10 to 10 raised to power at least 13 numbers per centimeter square. But yeah. So whenever the operations are desired, so it should be done in there. And assembly parts are checked for mechanical tolerance, and then they are ready for the tolerance, the machining tolerance, the mechanical guys. I learned those terms from mechanical guys, but if someone asks counter questions, I may not be able to answer. There are many symmetries for an assembly. The gun should not be tilted, should be parallel. The axial alignment of the components should be in microns, so that you have your imagination come to reality. So this is done, this marvelous job is done by our mechanical engineers. And once the tests are done, then we can surely say our design parameters are acceptable, of course, in certain ranges.
Is there a temperature induced mechanical stresses in the system?
Yes.
Because it's working high temperature.
Yes.
And
we had lots of accidents. I will discuss a couple of them in the end of side. One of them was twice they were more or less temperature induced accidents. Okay, is there any comment, question? Should we move forward?
And
I don't know if
to
it's
Shamsuddin question. They are manufactured at a certain temperature, and they quality assured also at the same temperature. Components. When you are talking of micron and
Yes.
micron things.
Yeah, but when the system is operating,
Yes.
since it is heated, cathode is heated from the back, the temperature rises very high over there.
The concentricity is very important. The total assembly. And once you assembled it, then those variations within it are sort of taken care of.
And of course, I may add to Professor's comment. We also conduct thermal analysis of our devices, especially in the electron guns. I didn't have time to cover this aspect in this presentation. Maybe special topic we can discuss if we have time later this week. But of course, you're absolutely right. The operational, one of the key ingredient of the design is the complete thermal analysis of the system. Okay, now I used last night I thought that I should go through an additional dose, but that dose has already been administered to you. Just imagine that we are now going to have a beam which is diverging. We have to have a lens to keep it parallel. This is where the parallelism comes. This is where the low emittance concept comes. And we have this concept borrowed from optics, as we were discussing yesterday. How this lens can be made in reality. We have an aperture, metallic aperture. I have given it a certain potential. Since this area, for example, is higher in potential than this area, then the potential lines will bulge towards the lower potential side and make a sort of lens. Okay, and the electric field lines which are perpendicular to this, the particles or the beam should follow this thing. Here's another example. What is written in green must remain in your mind at least for a few hours. Potential lines follow the geometry of the electrodes. This point is clear now. Okay, if this is all metallic, and I put some power supply to the walls, the potentials which will be established will follow the shape or the geometry of this room. Okay, and the electric fields are perpendicular to the potentials, and the charges that flow, they follow the electric fields. 3 points. Potentials follow the geometry. Electric field is perpendicular to the potentials, and charges are parallel to electric field. Just 3 points.
May I ask a question? This electron beam is coming from the cathode, or
It's just a cartoon from a book. It is just a charge.
you're assuming that they are parallel?
They are
each
parallel.
other?
Yes,
That's
this
the
is
reason I
because
asked.
this book, very precise book, was written by Helmut Liebel. It is one of the references that I suggested you guys to read yesterday. The book very extensively discusses the optics of the charged particles. So we assume that, say for example, because anyone who has taken course in optics, they say, okay, a line which is passing through the principal axis, a ray which has a certain distance but parallel to the principal axis, what will happen? It's just to build the theory. Okay. In fact, the charges which emerge from the gun, they're not parallel at all. If they are parallel, so there is no need to put lenses. Huh? If they're not parallel, they are going in fact, anywhere they want to. So yeah. So the physics design of electron guns. We have physics with us, but we have to design the electron sources. I will discuss 2 geometries: the conventional PS type electron gun, which follows this green law. Okay. You first establish the potentials, and then you try to use those potentials to have electron guns. But this design has many shortcomings, because as humans we are limited in knowledge, in technology, and that's where the innovation comes to. But yeah, then we switch to this approach. We start from the scratch. We say that, okay, some things which were not covered in the Pierce type geometry should be covered here. So this is a commercially applied technology scheme. Nowadays, in my humble knowledge, as far as I know, almost every commercial LINAC, that is Varian, General Electric, or some other company, Thales even, they use these kind of geometries for their application. It is very simple, but it has some flaws. Not so flaws. Someone can get annoyed, but it's like there are shortcomings physics-wise. But I would like to use my physics, or physicists would like to use their physics, to have something more comprehensive design-wise. So we will use the concept of para-axials, the rays which are parallel to the principal axis that you have pointed. We will design a source while we incorporate the space charge, and we give our constraints which are dictated by the end user and are mathematically translated in the form of the state vector. So we use those constraints to have all together a fresh theory of electron gun design. So we currently use this approach we initially used this approach, but we switched to this about 8 years ago. Okay, this is more or less a repetition, but in fact, I included this slide today because I deliberately skipped this important parameter, that is perviance. Someone was discussing yesterday that they are working on the design, in fact, manufactured some electron guns, at least in the laboratory. So to satisfy their understanding, I would say that we have a parameter called perviance. Have we heard about it, others? Okay, let me explain it to you. You have, let's say, parallel plates. We discussed this geometry yesterday, huh? This is when we were developing our understanding of the Child-Langmuir law, the law which governs the thermionic emission of very large amount of charges, the space charges. We discussed it yesterday. But are we going to have unlimited current once we apply a potential between these two plates, a cathode and anode is established? No, we are not limited to the supply. This I is the beam current, V is the potential that is applied, and P is the perviance of the gun. This is the geometry constraint. This is the geometrical constraint of a gun if that gun is operating in space charge limited operation. When I say space charge, it means that I have accumulation of the charge. I need this thing, by the way. Okay, so I have to live with this bunch, this cloud. But I am limited with this thing. This is a law, a physics law. We went to a detailed evaluation of this guy. So this geometrical parameter is very important. Let's discuss this thing in a bit more detail. The perviance is basically this constant. Vacuum is there. Everything is evaluated in vacuum. So you have to have an ideal vacuum that can never go to vacuum. So the vacuum is hidden in this parameter. This neta, I will discuss it. This neta is also related to the geometry, but it's also related to the beam profile. What sort of beam you want? Converging, parallel, or converging to a point, diverging. So this is hidden in the geometry. And simply the area of the cathode that you are using, for example, if you have introduced this part, you have dedicated, let's say, if this whole thing is 1 meter, just imagine, and this area that you have dedicated for emission is about 1 centimeter squared, then this is the active area A in this formula, and the spatial distance between the two plates. And this theory is only valid for parallel plates. So the limitation of geometry, it should be very clear. The limitation of the geometry, the theory is that this theory was developed for parallel plates. The evaluation could be only done in this case, but it's working commercially. People are earning thousands, maybe millions of dollars with this thing. What happens? Peers, I think I should go with this slide first. Imagine that you have 2 spheres. Spheres are concentric spheres. One ball is surrounding a certain inner ball, and I take out a slice of it. Okay, so inevitably you can think that the potential lines will follow the geometry. This is clear. Okay, so this will make a lens which is converging, and a beam that is coming out should be converging to a point. I mean, the collimation that is required by the designers. So if you realize this geometry in a real Pierce gun, then the gun assembly would look something like this. I think this picture should be understandable, this cartoon should be understandable to everyone now. This is the area which is emitting the electrons, okay? A in that formula. And this is the focusing, which is nearly the part of this concentric sphere. And the anode is giving a way to have electrons extracted and then injected into the actual machine. So what we'll do, because you have an aperture here, remember.
May I ask you again?
Sure.
The electron is coming from the cathode.
Yes.
Whichever part of the cathode.
Yes.
It comes in any direction.
In?
It comes in any direction.
Yes.
And it has a distribution of it too.
Yes.
Energy distribution.
Yes.
Can you expect how many percent of the electrons can be focused over?
Yes, I will show in this slide when we come to the distribution. Okay, so maybe step by step we will build the theory. Okay.
Another thing I would like to ask is the cathode surface is uniform.
For the sake of theory, it is. In reality, it's not.
Is not.
It's not. We are building theory, but yeah, for when we go to the reality, we will face. We do face all these practical situations. But physics, when you develop physics, we always go for some assumptions, and then we go for the actual world. So imagine that we have a very uniform thing, but since it was diverging out, we have already made our cathode in a concave shape, or the part of the sphere. Then the beam which is coming from the cathode is further focused by this focusing cathode, and because we have an aperture and this aperture is grounded, this is at a negative potential. This is negative potential, so it is like, in fact, given kVs of the potential, the essential potential that is required. So you can now understand the reason why these red lines, which are presenting the potentials, are making a diverging lines.
Select some kinetic energy very close.
Yes, so that's. So this is what a Pierce gun would look like in its very simple form. It has three regions. One is the region between the cathode and anode, where the emission takes place and where the actual acceleration or the selection of the particles are performed. Region 2 is basically the aperture, we have discussed it, and region 3 is a field-free region. It has to be field-free. A field-free means that they are now drifting, and the reason they are like diverging again, because they have space charge repulsion, mainly due to space charge repulsion and due to different vectors, x prime, y prime, this different slopes. That's why I wanted you to form that homework problem, because only then you can see that all the particles do not have uniform slope. Had it been the case, we would be very easy. But due to this intrinsic slope, they try to diverge. We have to put additional optics here. Okay. All right. So what happens that when the beam comes to this region 1? As we have already discussed, the beam will actually push the potentials, this diagram. Push. So no matter how precisely you manufactured your gun, the potentials are already disturbed. And remember that we started with the sphere, the radius of the spheres. Pierce has written many excellent accounts. People have further translated those geometries. They have discussed it. It is in detail in everywhere. But imagine, but to summarize, they are essentially part of concentric spheres. So we are limited with the choice of geometry. What do you think we should do in order to avoid this? Because ideally, this yellow part should be followed. This is the desired thing. But because electrons are coming, they have pushed the potentials. So due to the ray tracing concept, the actual flow is somewhat lesser focused. Okay? So what we do, we put an additional focusing lens to counter this effect. You see, this focusing lens has greater curvature as compared to this thing. You can appreciate the geometry now. It is focusing aggressively in order to focus the beam to its actually desired value. But this has to be, is it an art, it's an experience, or what? People did many experiments, and they came up with a number, magic number. That magic number is around 67.5 degrees. I call it magic number. This is my, well, we always discuss this number in our group, and I couldn't find a decent phrase for it. But magic doesn't work in physics. There's no world near real world which is based on magic. There should be a logic, but in fact, this was a starting point. So this shape, this is a very crazy shape. I mean, do you need, how will you first mathematically conceive this? How will you tell your mechanical engineer that I need this sort of profile? Is it just an art, or it has a solid physical background? But they said, okay, if after many experiences, years and decades perhaps of experimentation, they came up with this number that, okay, if you have a focusing electrode that is around 67.5 degrees inclined, then you will have a reasonably good beam, a beam which is reliable, which is commercially acceptable. And then they said, okay, this thing is there. All right, we are not finished with the problems of this geometry. This is the problem that is actually happening at the cathode. What about the anode? We have an aperture, but this aperture is basically acting as a diverging lens, the red line. So the beam which was supposed to focus here is actually focused downstream. Okay, so this is also a defocusing effect that is inherent, always there with this sort of geometry. Now, the question Professor mentioned very rightly. Suppose we have a source which is sitting here, and these red lines are showing the emission pattern of the source. We are familiar as physicists with this kind of distribution. This distribution is telling us that electrons are not emitted with single energy. There's always the distribution, thermal distribution, Maxwell's distribution. That's anyone who has taken the course on statistical thermodynamics is familiar with this concept. So this is what is the actual scenario usually is. And the lenses that no matter how good you design, no matter how precisely you manufacture, the total area that you can cover is maximum 2 sigma, that is 95% of the population that is covered. So you cannot have a lens that will cover everything. it's a loss. Loss in terms of current, loss in terms of emittance, loss in terms of J being the current density. So non-uniform emission from source is also a serious source of non-uniformity, misalignment, aberrations, and over the period of operations, you see some spots are emitting more and others are less. So there are craters forming on the cathode surface. The cathode, as the cathode ages, as the electron gun ages, it is it's very difficult to operate that kind of gun. So it is nearly at the end. We say nearly at the end of operational life. You can donate it to some student, but for commercial application, it's not okay.
I have seen that ion propulsion, they are using the needles.
Yes.
Have it right, the needles on the surface of the cathode? Because at the point of the needles, the electric field is higher, electrons come in here.
Yes, the particular application you're mentioning, sir, is, if I understand correctly, is the ion thrusters. And their aim is to have very high current density in order to neutralize the xenon ions or the argon ions that are coming out. There, you're not bothered about the collimation. You have to have a shower of electrons. So needles have needle-like structures. They have their many applications, which I have gone through. They use lanthanum hexaboride as the source of the electron sources. They are operated at higher temperatures relatively to the thermionic guns. Number one. Number two is that they have pointed structures because the points, of course, has higher concentration of the electric field. So there's lots and lots of chances, statistically speaking, chances to have field emission from that point. In fact, I feel that many of our attendants, students and audience are interested in ion thrusters and the application of electron guns in that. Maybe in the afternoon I can have a couple of slides dedicated to that topic, but unfortunately I didn't include it here. Maybe in the afternoon I can have a more detailed sort of briefing on this topic.
Can be used in microscope.
Yes, in microscopes, SEMS, secondary electron microscopes. There, the current needed is not much. In fact, the ones which we have in our institute, they had those Mitsubishi filaments, the pointed filaments, the tungsten, corrugated tungsten in many cases. And the current was at maximum microamps. That is enough for imaging, but for applications like microwaves, you need high current. So the people shifted. It depends, of course, on the need.
I should ask a similar question. Is this Maxwellian distribution?
Yes.
Similar in the other modes of emission, like field emission and others? You partially answered this question, but is this question general valid for other?
It is valid for thermionic.
Thermionic.
Okay. So, shall we move forward? We have time, is it?
Yes, 3 minutes. I think we can break. We can take a break.
I'm very slow. Anyways, let's have a quick ending or a reasonable ending to this PS type gun, and then we switch to this. So let's be patient. So this is how the operation of the beam is done in terms of PS type. You have to apply negative potential to your electrodes and very high potentials to the focusing, and the anodes are grounded. But since you have fields pushing electrons pushing the potentials, and depending upon the the amount of current that is extracted, sometimes you have to put additional feature on this part. So you see, this thing has maybe lesser current. If you go higher in current, you have to additionally focus it because the potentials will be pushing. And then perhaps if you go for very high end applications, for example, you have guns which are being operated at 150 kVs and maybe 300 kVs. We did some simulations for Tarla. The gun they have is designed to operate at 300 kilo electron volts, and it is pulsed. It is a very marvel of equipment, but it's equally tricky to operate because you cannot operate this in diode mode. You have to modulate you have to apply the potential in phases, in steps. So you have an additional anode. For example, if the total potential between cathode and anode is 200 volts, so 200 volts in a small space cannot be applied. I mean, it's a hell lot of voltage, kilos. So it is DC especially. So you divide them in reasonable parts, but equal effect is same. So yeah, the beam profile from the PS type gun looks like it doesn't look very convincing. I mean, it looks convincing, but it has some features that can be improved. So in next few minutes and then next talk, perhaps we will be devising a theory based upon of the knowledge that we gathered yesterday and bit in this morning, to have our own design of this geometry, which mitigates the shortcomings of this design. This brings us to a new idea. Go through this slide while I take a sip of water. Now the idea is, okay, let me go through that, or let me just give you a short flash of the memory. You remember that green part? I said potentials actually dictate the geometry. It is right. It is right. But let me go through a technique. I want a certain trajectory. It is my desire. Someone is supposed to design the potentials accordingly. It is the inverse of the approach that Pierce adopted. We go in the inverse direction, and it solves many of the problems that were faced in the Pierce thing. So the idea is the electron trajectory follow electric fields, that is the potentials. Understandable. Potentials follow the geometry. This is the previous lesson. Now let us devise a scheme where geometry is designed for a particular beam trajectory. The boss is now the trajectory, not the geometry. They are, of course, coupled physically, but design-wise, let's disintegrate them. And now we shall go after this ideology where the trajectory will actually dictate the geometry of the system. We can take a short break, maybe 10 minutes. 15? Okay. 15 minutes, and then we go to the physics of the guns. So